So far we have looked at creating junctions and some of the basic ideas behind how to draw band diagrams. So we will now start a formal approach to the metal semiconductor junction. So a metal semiconductor junction is quite important because if you think of any device, so let us say you are building a transistor or you are trying to build a device wherein you want to have these metal contacts and you want to actually apply a voltage or send a current through this device. So this is your semiconductor device. Now how do the properties of this metal contact and this semiconductor affect the current voltage characteristics? Okay. Ideally what we would like is we want to think of these contacts as very ideal contacts. They should offer no impedance and they should very faithfully transmit any voltage applied to the metal and onto the semiconductor. But that is not really true, and in fact depending on the kind of contact you make between the metal and semiconductor, various things could happen. So therefore the study of having a metal and interfaced with the semiconductor, that is to create a metal semiconductor junction is quite important. And what we will do here is first look at get some qualitative estimate as to what the different metal semiconductor junctions might look like depending upon the work function differences between the metal and semiconductor, and draw the band diagrams for these kind of contacts. And then we will get into a bit of detailed analytical calculations on estimating the impedance and the particularly the capacitance of a metal semiconductor junction, and also the current voltage characteristics in a metal semiconductor junction. Okay. So first let us start with trying to draw some band diagrams. Okay. So first let us take the example of a metal and an n-type semiconductor where the work function of the metal is greater than the work function of the semiconductor. So we when we looked at the different materials before, we noted the fact that the electron affinity of a semiconductor never changes. Okay, that's always fixed, whereas the work function of a metal is also a fixed parameter. So irrespective of the kind of contact you make, the work function of a metal and the electron affinity of the semiconductor will not change, okay, at any location in space. So now let us try to redo this problem. We used this as an example when we discussed the brief study of junctions, but let us come back to this problem, which is we have a metal which has got a work function of q phi m, and we have got a semiconductor which is n type. So it is an n type semiconductor and it has got a Fermi level slightly above the mid gap, slightly above EI, and it has got a work function of q phi s. And the key is in this particular case your phi m is greater than phi s, which means that the Fermi level of the metal lies further away from the vacuum energy level as compared to the Fermi level of the semiconductor. So let's see what happens when we make a contact between these two. Now using our old analogy, which is that of water in a bucket, for whatever use that analogy is, we do realize that since the Fermi level of the semiconductor is located above the Fermi level of the metal, it is very likely that the semiconductor is going to transfer electrons to the metal. And the second thing is the Fermi levels will align as long as we are in thermal equilibrium. So once you make this contact and keep it at thermal equilibrium, the Fermi levels align. So that is the common Fermi level for metal and semiconductor. Far away from the contact, the semiconductor does not see anything interesting. It is exactly the way it would be, and this is called as the bulk region. Okay, this is called as the bulk, and this is called as the interface. And since the semiconductor gave up electrons, to the metal, the conduction band has to move away from the Fermi level near the interface. So the this region of the semiconductor has lost a lot of electrons, and therefore the conduction band edge at this region of the semiconductor moves away from the Fermi level. In order since n is equal to capital NC e to the power minus EC minus EF by KT, if when n goes down, it implies that this term increases because there is a negative sign here. This term has to increase. So, EC minus EF has to increase, and therefore, the conduction band bends away from the Fermi level. So, the band bending diagram looks like this. So, you have the metal Fermi level, and at this point at the junction there is a massive barrier, okay, and we call that barrier height. That energy of this barrier is denoted by a special symbol which is called phi b, and that is the potential, and q phi b is the energy. And after this there is the bands bend away. So, you can see this gradual bending of the band, and to a point beyond which the semiconductor does not see any band bending. So, the region of the semiconductor which does not see any band bending, okay, wherein the semiconductor does not even realize that there is a metal semiconductor junction, is called as the bulk of the semiconductor. Okay. So, when we say bulk, we automatically imply that the region of the semiconductor far away from the junction. And if you look at this contact, okay, so let's think of it. Let's assume that we have established this kind of a contact in order to study a semiconductor, in order to electrically excite a semiconductor by sending in some current and some voltage. Now, how good is this contact? So, think about the majority carriers in the semiconductor. So, we have electrons in the semiconductor. There is an n type semiconductor. We have plenty of electrons and very few holes. Okay. Now, and you think of the electrons in the metal. Okay. So, let us say the electron in the metal has to get past and get into the semiconductor. What does the electron see? It sees a massive barrier. So, as we discussed earlier, the band bending diagrams are drawn such that the higher potentials lie at lower points. Okay. So, what I mean by that is, let us say you have a Fermi level. Okay. So, let us say you have a metal and you got a Fermi level, and you start increasing the voltage of this metal. So, what would happen is that the Fermi level will start moving downward. Okay. So, if you see two energy levels in an energy band diagram, then the level that is lower has got a higher electrical potential. So, that is just the way it is drawn. So, that is just convention. Okay. It is drawn thinking of the electron as rolling downhill. Okay. So, if you have electrons, the electrons would like to roll downhill towards the higher potential, and the holes would like to roll uphill towards the lower potential. Okay. So, you can think of electrons trying to roll downhill. Now, if the electrons in the metal, they see a massive barrier here. It is like a huge cliff. It is not very friendly for an electron that wants to get across. Okay. So, therefore, it is not going to help the conduction. It is not going to be very easy to have straightforward drift conduction. Okay. On the other hand, what about the electrons in the semiconductor? The electrons in the semiconductor also see a barrier, right. So, not as steep as that of the metal, but they do see a barrier because they have to now roll up the hill in order to get into the metal. So, therefore, this kind of a contact is not going to give you an ohmic nature, in the sense that an ideal contact. So, you would have a metal and you would have a semiconductor, and if you want to model this ideal contact, we would at most want to see a resistor there. So, that's about it. So, we would like a contact to be like this, so that any voltage I apply in the metal is going to have and let us say I send a current through this contact, there is going to be a small voltage drop across this contact, but generally the IV characteristics is linear. It is going to behave like a small resistor. So, that is the contact we want. Okay. But here that is not the contact we are going to get. Okay. In fact, this contact has a rectifying nature. Okay. So, I will tell you what that means when we look at the current voltage characteristics. It's got a rectifying nature, and it is something called as a Schottky contact, or a and this barrier is something called as the Schottky barrier. Okay. So, it is not a contact that is going to give you an ohmic relation between current and voltage. Okay. But nevertheless that is the contact you get. Now, what happens is, in reality, because a semiconductor metal, any interface with the semiconductor has got a lot of trap states, because that is a place where you have cleaved off the semiconductor, and or that is a place where you have impurities, and therefore you have a lot of energy levels sitting inside the band gap. So, because of that, the Fermi levels are not free to move around. Okay, and the Fermi levels cannot move around in the as easily as described by the mechanics we discussed for the band bending, and therefore you have something called as a Fermi level being pinned, and due to that you have a lot of interesting effects that come up, and it so happens that more likely than not you will end up with a contact that might be rectifying. Okay. So, in many practical cases this is the kind of contact you might actually get, and that is the best you can probably do. So, how do we build good devices with such a contact, because we have already seen that this kind of a contact is not going to be very friendly for electron transport. Okay. So, so because of that we will pay special attention to the Schottky contact and look at the current voltage characteristics of this contact and study what the impedance is, etc., and think about mechanisms by which we can improve the nature of this contact, so that we can use such a band bending to our advantage. Okay. So, but anyway, so now let us just proceed and try to look at all the other possible combinations. So, this is the N type semiconductor with the metal with phi m greater than phi s. So, that gave you this kind of a band bending diagram. So, let us take a look at the band bending again. So, the bands, the EC, the conduction band edge, moves away from the Fermi level, and it slowly bends back downwards and approaches the bulk condition, right. So, till this point we could say that there is band bending, and beyond this the semiconductor does not see anything interesting. Now, if you think about this region here, this region in the semiconductor here, okay, what does it have? The region initially had a lot of electrons because it is an n-doped semiconductor, but after the semiconductor transferred electrons to the metal during the contact formation, and after the creation of this band bending, you will see that this region does not encourage or does not have too many electrons, at least particularly very close to the interface. So, the electron count here is now sparse. The whole count is anyway very sparse because it is an n-type semiconductor. Okay. Therefore, this region is in some sense void of free carriers. Okay. Now, void is a very powerful word. It does not mean that there are absolutely no free carriers. What it means is that the free carrier count is much smaller compared to the static charges present in this region. So, what are the static charges? So, since it is an n-type semiconductor, we had initially doped the semiconductor with a lot of donor dopants, right. And at 300 Kelvin the semiconductor is extrinsic and all the dopants are ionized, and what we have is fixed positive charges in this n-type semiconductor. Now, these charges cannot move, they are a part of the lattice and they are all fixed, and these ionized donors, they gave up an electron which had become a part of your free carrier concentration. Now, this donor dopant concentration, these ionized charges are, how many of them are there? We have Nd per unit volume of this. Okay. So, that is the number of ionized charges that we have, and since the semiconductor gave up some electrons to the metal, and since the bands are bent in a manner that encourage the electrons to stay away from this region has got very few electrons as compared to the bulk. Okay. Now the bulk has as many electrons as Nd, and this region has got much smaller number of electrons as compared to Nd. And in order to quantify the number of electrons, what we need to do is identify the Ec minus Ef at every location, and we will know the exact count of the electrons. Therefore, since this region has got very few free carriers, okay, holes are anyway low, this region is said to be depleted, okay, and this region is called as the depletion region of a metal semiconductor Schottky contact. So this is a technical term, and it is something that we will use quite often. Now if you make the assumption that this region has only fixed ions because of the donors, the ionized donors, and it has got no, or it has got very negligible N and P, then the assumption that is made is called as the depletion approximation or full depletion approximation. Now how good is that approximation? Okay. Near the interface it is probably a reasonably good approximation, but as you start moving towards the bulk, okay, so let us look at this region here, look at the Ec minus Ef, and let us look at this region here, look at the Ec minus Ef. The Ec minus Ef here is say much larger than the Ec minus Ef in the bulk, and since it is an exponential dependence of on Ec minus Ef for the carrier count, we can say that here the N is really very low, and it is much lower than the N in the bulk. But as we start approaching, as the bands bend and the bending gets more and more gentle, and as it starts approaching the bulk, this approximation begins to fall off. For example, we cannot definitely make that assumption at this interface because we are at the bulk. Okay. So you need to be very careful as to when and where these approximations are made. Now these kind of approximations are very helpful in sort of simplifying the mathematics. Now in this course we will consider both aspects. Okay. We will first simplify the mathematics to get a gauge on how the device behaves, etc. We will make use of such assumptions. Okay. But then we will also try to be very careful and point out how we can calculate all these answers out with all the great details. Alright. So now let us just proceed. So let's move on from the Schottky contact and proceed towards the other kind of junctions. So let us say we again have a metal semiconductor junction, and let us say the semiconductor is still an N type semiconductor, but this time we will let the work function of the metal be less than the work function of the semiconductor, which means phi m is less than phi s. Okay. So in the previous case we had phi m greater than phi s. Now since phi m is less than phi s, the metal will start providing electrons to the semiconductor. Okay. So it's like two buckets with water level higher here as compared to the other one, that's the semiconductor bucket and this is the metal. Okay. So I think this is the last time I will try to use the bucket analogy. We need to refrain ourselves from heading towards that. Okay. So if you create this junction, the metal will give the electrons to the semiconductor. Once again the Fermi levels will align, the metal will give the electrons to the semiconductor, and since this interface has now got more electrons as compared to the bulk, the conduction band will bend towards the Fermi level instead of away. Okay. So the band bending diagram will look like this. Okay. So you have the metal, the Fermi level is aligned. Okay. In the bulk the semiconductor does not know what is going on, it sees no change or it does not seen anything specifically interesting, and therefore everything is as it should be, and this is the bulk region. But close to the interface, since the metal pushed the electrons into the semiconductor, the conduction band bends towards the semiconductor, towards the Fermi level, sorry. and the valence band follows that bending because the energy gap is fixed. Now this means that this region has got excess, it's got more electrons as compared to the bulk. Okay, so this is the electron count here is greater than the bulk. So most definitely this is the exact opposite of your depletion region, right. This is definitely not a depleted region, it's got a lot of free carriers, and more interestingly you see that the bending is now favorable for electrons to move through. Okay, the electrons can easily roll down the hill, and they do not see much of a barrier in either direction, and you have an easy migration of electrons across from the metal to the semiconductor. This is very much against what we saw. This is very much the opposite of what we saw in the case of a Schottky contact, wherein we saw a barrier of this kind. So the electrons in the metal saw this cliff, and the electrons in the semiconductor had to roll up the hill. Okay, but here it's a very different scenario, and this is the kind of contact that we would ideally like. Okay, so if you were to make a contact, okay, between a metal and a semiconductor, and let's say this is an n-type semiconductor, and you make a contact with a metal who's got a work function less than that of a semiconductor, then you should ideally end up with something called as an ohmic contact, because here the electrons can easily move across through from the metal to the semiconductor and vice versa. Now let us go ahead and consider some more examples. Now we will again consider a metal semiconductor junction, but we will consider a p-type semiconductor. So p-type semiconductor has got a Fermi level that is located closer to the valence band, that is the major difference. And let us take the case of phi m being greater than phi s. So this is your q phi s, that is the work function of the semiconductor, this is the work function of the metal, and since q phi m is greater than q phi s, the Fermi level of the metal lies further away from the vacuum energy level as compared to the semiconductor. So now what would happen? So this is a p-type semiconductor, the majority carriers here are the holes. Okay, there are very few electrons, very few electrons, and a large number of holes. Okay, so you have heavily it's a large holes are the majority carriers here. So if you were to create a junction, the first thing is of course the Fermi level will align. Okay, but then where do the electrons go? Since the Fermi level of the semiconductor is higher than the Fermi level of the metal, the semiconductor will give electrons to the metal. Okay, there are not very many of them, but the semiconductor will try to give electrons to the metal. So what would happen in that case? If the semiconductor gives electrons to the metal, EC minus EF has to increase, and therefore the conduction and conduction band edge will try to move away from the Fermi level. So the band bending would look like this. Okay, so you have your EF, the EF is aligned, but since the semiconductor gave electrons to the metal, the conduction band edge moves away from the Fermi level and the valence band edge follows. Now what kind of a contact is this? Is this a contact that is going to aid our charge transport or not? Okay. Now if this were to be an n-type material and you saw this kind of a barrier, it is definitely a Schottky contact, but here the majority carriers are the holes. So we should not worry so much about the electron movement across this junction, but rather look at the movement of holes, and the holes love to run up the hill and they see a very nice gentle slope wherein they can easily move and migrate into the metal. So what about the metal? So the movement of holes into the metal simply implies that the electrons at this interface recombine, therefore leading to an effective electron flux in this direction. So there is good charge transport between the semiconductor and the metal, and this is once again an ohmic contact. So this is again a kind of contact you would like to have. So if you have a p-type semiconductor and you want to make an ohmic contact with a metal, you must choose a metal which has got a work function that is greater than the semiconductor. Alright, so this is an ohmic contact with a p-type semiconductor. And far away in the bulk you see that it is still a p-type semiconductor, the EF is close to EV, and the semiconductor sees nothing interesting. Finally, we will take the fourth of the cases. Okay. It is a metal p type semiconductor junction, but phi m is now less than phi s, which means that you have your p type semiconductor. Okay. So, these are all energies, so it should all be q there. You have a p type semiconductor, that is your Fermi level, it is close to the valence band edge, that is my q phi s, and phi m less than phi s implies that the Fermi level of the metal lies closer to the valence band edge, and therefore, this is the situation. Now, if you create a contact, you will align the Fermi levels as usual, but now it is going to be the metal that transfers electrons to the semiconductor, because the metal has got a higher Fermi level as compared to the semiconductor, and therefore, the bands in the semiconductor will now, the conduction band will now bend towards the Fermi level, because the semiconductor has accepted electrons and there is a large electron population here. So, the band bending will look like this. Okay. So, you have the Fermi levels that are aligned deep in the bulk, there is nothing interesting, it is still your regular p type material, but at the interface the semiconductor has increased its electron population, and you find that the conduction band bends towards the Fermi level because of this increased electron count. But then what kind of a contact is this? So, since holes are the majority carriers, let us look at what the holes experience. The holes now see a barrier, they have to run down the hill. Okay. So, in the previous case the holes could run up the hill and into the metal, and it was a nice ohmic contact, but now the holes have been asked to run down the hill, they do not like it and they see a barrier, and therefore, this is very much like your barrier or a Schottky contact which we discussed earlier, but the only thing is that the barrier is now formed in the between the Fermi level of the metal and the valence band edge, and that is your barrier there. Okay. So, just to summarize, we considered 4 kinds of contacts. We took a metal with an n type semiconductor, and we considered the case of phi m greater than phi s and phi m less than phi s. In the case of a metal, in the case of phi m greater than phi s, we found that we ended up with a Schottky contact or a rectifying contact. In the case of phi m less than phi s, the metal gave electrons to the semiconductor and we ended up with an ohmic contact. In the case of a metal p type semiconductor junction, when phi m was greater than phi s, we had an ohmic contact, because we are now looking at what the holes are doing at the valence band, and when phi m is less than phi s, we ended up with a Schottky contact. So, that is a summary of the 4 kinds of contacts that we have established, and what we will do from this point on is to study the electrostatics and the current voltage characteristics in each of these contacts.